Okay, so this talk is about actually 5G, and it will be focusing mostly actually on 6G. And the title that I would like to share with you now, that you see on your screen, is 6G networks, hyper connecting the connected and connecting the unconnected. So as you can see from the title, I am right away kind of putting the two messages I would like to convey as part of this talk, which is the vision of 6G, at least in our view. This vision has two components. A component where basically we try, uh, you know, going along the same lines of the previous generation of wireless communication system, that we're trying to kind of push the envelope by hyper connecting or super connecting the connected. And then there is another dimension which is often forgotten, which is trying to connect the people that are unconnected. And actually, as you will see in my talk, it's another important aspect that has been more or less neglected as part of the previous generation of communication system, although there has been some improvement. So the outline, and that's how the link to 5G comes. The first kind of part I would like to kind of discuss is what has 5G been, and then what might 6G be. So this is a little bit controversial because like most people are just starting talking about 5G, as you see that in the news media, early deployment worldwide of 5G are being discussed. But from a research perspective, we have been already quite active in 5G for the last 10 years. And now actually is the time to start brainstorming, start thinking about what 6G is going to be, with the understanding that 6G is going to be pretty much deployed 10 years from now. So with this introduction, I would like to highlight to you what we think are some important 6G technology trends. And then I will focus on what I mentioned earlier as one of the forgotten mission of wireless communication over the last decades, which is this aspect of lack of global connectivity, or like the problem where there are many regions in this world that are still lacking good connectivity. I will give you some example of how we can improve global connectivity through, for example, optical wireless communication. And that's why I'm using this kind of catchy line here, a light in digital darkness. So people talk about digital divide when basically we are having region where a lot of people are unconnected. And we hope that with some of the optical wireless communication capabilities, we'll be able to connect these unconnected people and bring some light to this digital darkness. I will then conclude the talk with some summary of the main results. Okay, let's move on. So moving from 5G to 6G, this is just the big context. The big context or the big motivation of all our work, obviously, is this kind of continuous increase in the number of subscribers worldwide, this continuous increase in the number or amount of data being transferred wirelessly. It's quite impressive to see this kind of continuous increase in usage, both in terms of number of users and in terms of data that is transferred wirelessly. And because of that, obviously, this continuous traffic increase is pushing the capacity limits of wireless networks. And this has been our interesting story as wireless telecom engineer over the last 5 or 6 decades, where we have seen the first generation of system in the 80s start with just simple analog voice communication system, evolve over different generation. Every generation takes about 10 years to be developed, to mature, to be deployed, eventually to be terminated, or at least to be phased out, so that the next generation comes into the place. So as you notice, we are now in 2020, which means we are at the early stage of 5G deployment with the three main characteristics of 5G: enhanced mobile broadband, massive machine type communication, and ultra reliable low latency communication. These have been the three important user scenarios that have been identified as part of 5G. And we have, as I mentioned earlier, 10 years ahead of us, so that by 2030, we'll be deploying 6G. So 6G has been kind of an interesting topic over the last year or so. Quite a bit of activity in terms of, let's say, workshops, special issues, conferences, research fundings. So here I'm kind of summarizing some of the initial initiatives that looked at 6G. There was, in particular, in March 2019, in Finland, the first 6G summit. It was very successful. The second summit happened last month, March 2020. It was supposed to be interactive and in person, but as you know, because of the pandemic situation, it has been kind of moved into a fully, let's say, virtual summit with a lot of interesting talk about the vision of 6G. So to summarize what 6G vision is, and there are many people speculating, of course, about 6G because still at the very early stage, we can say that one aspect of 6G is going to be what I call pushing the envelope, going for basically more advanced applications using wireless communication, like autonomous car driving, e-health. Like this is a perfect kind of example of a technology that can help us in this very exceptional era or age of pandemic, or like with the COVID-19. So you can think, like for example, as an example, you have a patient and the patient is infected. Doctor is scared or to be infected himself or herself. So the idea here is to minimize the contact between the doctor and the infected patient, and to have all this interaction be done through robots. And the medical doctor will be in a different room, like with joystick and with some good camera and computer vision capabilities in the room, being able to connect in a nearly kind of seamless way with the patient, and even maybe take some tests, or maybe even doing some surgery if needed, without having to be facing or interfacing with the patient and be subject to be infected. So, the idea here is there are a lot of applications can benefit from communication technology, and 6G is supposed to push this to the next level. So as I mentioned, there are a lot of speculations at this stage. A lot of us in the community have written paper. We had our share of speculation. We wrote our own perspective or vision paper. It appeared a couple of months ago in Nature Electronics. It's available on the net. It's called What Should 6G Be? You can download it and you can look at it. And it's like a vision paper on how 6G can push the envelope. But there is another important aspect that one has to look at, is that we are living in a world that is evolving rapidly. It's a world that basically is increasing in terms of number of population. It's a world that basically there is a big move, and in a way unhealthy move, from rural environment to urban environment. So now more than half of world population is living in urban environment. By 2050, it's expected that 2/3 of world population will be living in urban environment, and only 1/3 is going to be living in rural area. And then it is also projected that we are having more and more of these mega cities with more than 10 millions, with a kind of a predicted number of 43 million, 43 mega cities by 2030. So all of these are kind of trends that are not very friendly and that are pushing people to look at ways to remain sustainable, although we are growing in this fashion. And you may have heard about the so-called Sustainability Development Goals. These are very noble goals that have been established and voted by the nation that form the United Nations. The idea here is to kind of aim to kind of fight poverty, fight hunger, try to kind of reduce inequalities between people, try to kind of be friendly to the environment, and so on and so forth. There are 17 of these goals. They are all, as I mentioned, very noble. And the objective is to globally, we achieve some, if not all, these goals by 2030. So we have 10 years to achieve these goals, or at least move towards the positive direction in the achievement of these goals. So with this perspective and these SDGs or Sustainable Development Goals now in place only recently, like a couple of years ago, one important statement that we can make is that although the previous generation of wireless communication system were essentially driven by mobile network operator, essentially by profit, by financial considerations, our hope that 6G will be driven at least in part by these sustainability development goals, which means that while 6G should still target improved efficiency, better power efficiency, better bandwidth efficiency, better capacity, it should also try to be more inclusive. It should try to connect a bigger fraction of the world population. Of course, although it's beyond the scope of this talk, 6G has to be even more secure and even more safe than what 4G and 5G are today, because 6G is expected to be part of our lives in an even more important way, and we'll be relying more and more in every single transaction or every single kind of activity in our life on wireless communication. So if you will, this is a diagram that is typically used to summarize 5G. It shows the three important user scenarios: in blue, enhanced mobile broadband; in green, ultra reliable and low latency communication; in pink, massive machine type communication. What you would like to add to this kind of three user scenario that in the context of 6G can be combined together. You can have blue and green. So you have enhanced mobile broadband with ultra reliable low latency communication, let's say for broadband gaming application. But on the top of that, on the top of these pushing the envelope kind of applications, we would like actually to go for something a little bit more basic, which is basic internet access or global access to the internet for all, known as Gaia. Connecting the unconnected kind of people in this world is another important mission of hopefully 6G. So let us now look at some technology trends that are going to make 6G happen, and then go back to this kind of second mission of 6G, which is connecting the unconnected. So as you know, for any generation of wireless communication system, one big aspect is spectrum. Spectrum is a natural resource, it's limited. We need to basically fit within this limited spectrum. And as such, there has been quite a bit of research done over the last 4 decades or 5 decades, how to improve generation of system to improve what is known as the area traffic capacity or area spectral efficiency, measured in bit per second per meter square. So that's a very simple metrics that you can kind of divide by multiplying up and down by node and by hertz into 3 factors. beat per second per hertz per node in red. That's what we know as a spectral efficiency. That's essentially the amount of data you are able to squeeze within this tube or this highway of information connecting a user to the closed access point. Then there is in blue node per meter square or the network density, and eventually there is in green hertz, which is the spectrum. So if you live in this kind of a small world down here on the left, and you want to go to this bigger world, this bigger circle that has a much better performance, you need to improve along these three dimensions: the red, the blue, and the green. Now, looking at it from this perspective, you can obviously look at different, let's say, technologies that have been pursued over the recent years. So, for instance, if you are trying to improve spectral efficiency, you'll be looking at applications such as massive MIMO, interference management, artificial radio space, and I would spend quite a bit of time explaining what it means. If you want to densify your network, you want to go for spectrum sharing, small cells, D2D communications. And if you go or want to go for more spectrum, obviously you can go to the upper part of the spectrum, millimeter wave, terahertz, and even optical part of the spectrum to be able to capitalize on the larger bands to communicate. So these are some of the technologies that are being pursued worldwide to make 6G happen. Let us talk about one very specific technology that emerged over the last few months. It's known by some of us as smart radio space. So what does it mean? It's in a way a natural evolution of communication theory. So those of you who took like a basic communication class as part of your undergraduate studies, you remember that typically the first thing we start with is optimizing the receiver, and that's how research in communication theory started, is how can we optimally detect a symbol in presence of noise at the receiver stage. This is how the work of match filter and so on has been kind of developed in the past century. And then at some point in the 90s or late 80s and 90s, people start looking at transmitter optimization. So you assume that you are able to know, estimate, or predict the channel ahead of you, and then essentially try to come up with optimal precoder or optimal transmitters. So at this stage, we are at the age where basically we optimize both receiver and transmitter. And obviously the next stage, which is the age of artificial radio spaces, the question that you'll be asking yourself is, what about if I change the channel that is connecting the transmitter to the receiver? How can I influence the channel to create a friendly end-to-end environment and improve my end-to-end quality of service? In other words, how to make the propagation channel more favorable to satisfy certain quality of service. Now, one way to do that is through what is known as reflecting intelligent surface. This is illustrated in the figure on the right. So you see a base station trying to communicate with multiple users, and you have this reflecting surface that is basically attached to a building. And the only thing it does basically reflect incoming signals, and it kind of change the phase of every single element in a way to focus the beam on particular user of interest at the other end. So it's a quite popular topic. We have been looking at that ourselves in our research group here at KAUST, and we looked at ways to optimize these phase shifts, or these reflectors. They are just basically a collection of passive, low cost, low energy consuming reflecting elements that, as I mentioned, are attached to certain buildings or surfaces, and they help users that do not have a good line of sight with a base station like illustrated in this figure to get a virtual or non-direct line of sight via a reflection. They act in a way, to simplify things, like a mirror. You can think of a situation where you have a light source trying to communicate with users where there is a wall in between, so there is no good line of sight. But if on the side you have a mirror, you can take advantage of that mirror to reflect that light, so that essentially you can bypass the kind of obstacle between the light and the receiver, and basically you can reach this receiver or this end user through this indirect path created by the mirror. It's exactly the same kind of mechanism that is being invoked here to connect user through this indirect line of sight. Let me show you some examples and show you the potential of this approach. So obviously here I'm illustrating a situation where I have a blockage or an obstacle between a receiver and a transmitter, but then I'm taking advantage of this reflecting surface to create a non-direct line of sight through this mirror or this controllable reflection surface. Now, the idea here was to try to see how can we move from that to, let's say, a network deployment perspective, and what kind of the potential advantage of this approach. So here, let me show you through this figure what we mean. Let's assume that we are at the center of this figure, having a base station, that's the cross, that is here, trying to talk to different points within this coverage area. Now we assume also that we have obstacles like buildings in this area, and every time there is a building or there is an obstacle, that anything in behind is not connected because it doesn't have a good line of sight. What you notice? You note that essentially anything that is unblocked is going to be green. It's in areas where we are able to communicate comfortably. Anything behind the obstacle will be obstructed and will be a red zone. Now, what about if we decide to move this particular surface on the top of this building into a reflecting surface and then allow it to kind of defy a Snell law and reflect in all kind of angles? So it doesn't have to be incident angle equal reflecting angles. If this happens, you move from this kind of setup where we have a lot of red spot in the upper part of the figure to many of them being cleared and being now accessible from the base station through basically this reflection. So that's the power or the potential of this reflecting surface. They allow you to illuminate many more points within your coverage area. So we did the study with, so basically, just to summarize what I just said, this in green is an area of coverage, in red an area of blockage, and we moved from this kind of situation before reflecting surface to something like that, a much better and much wider coverage area. Okay, now let's see what like the analysis we did here is, the question is, how can this reflecting surface help improve coverage in general? So we start here is like stochastic geometry based kind of approach. We have a coverage area of 1 kilometer by 1 kilometer. We have like we assume that we have a Poisson point process of 10 base stations per kilometer square. Another process kind of modeling the buildings density is 500 buildings per kilometer square. So obviously we assume at the starting point there is no reflecting surface, and you have all of these red knot spots, areas where you have no coverage or very bad coverage. These are all in red because there is a lot of obstacles on the way. Now what we're able to do with our analysis, if we increase the percentage, and these are randomly picked, but to increase in a random way the percentage of reflecting intelligent surface, then we move from this setup to this setup, much less red knot spots. So just by moving from 0% to 5% of RIS, we are able to do much better in terms of coverage. Now, if you go from 5% to 10%, you end up having only 4 knot spots in this whole area. You go further and you go to 40% of RIS, you end up with no, basically not spot. This is the potential of RIS. They allow you to increase quite a bit your coverage without the need to increase your power. This is only through reflection. So we're able to quantify that. That's so basically not spot area per kilometer square. And you see essentially that they decrease quite a bit as the fraction of building equipped with RIS increases. So this is essentially one of the nice things about NIS. Similarly, we showed here how we can increase coverage area. As the RIS percentage increase, you go more and more towards higher coverage probability. So if you will, this is what we started with without RIS in terms of coverage probability. If you increase the RIS, the percentage, then you end up having a much better outage or coverage probability. Now, what else can we do with this reflecting surface? We can, in a way, look at a variety of other interesting problems. For instance, here we show a situation where basically one reflecting surface is not enough because we have double blockage. So you can have double reflection to be able to reach a particular use in a tough spot. So you can kind of route through different reflecting surface to reach particular notch spots. Some other interesting research direction is that sometimes you want to get diversity, and you can achieve that by having multiple reflection coming from multiple reflecting surfaces. And then actually you can also take advantage of reflecting surface not only to improve your coverage from an SNR perspective, but also by reducing the interference. So you have a user here connected to this base station, another user connected to the second base station, but because of proximity, we are seeing that this base station is interfering with this user. But this base station knows exactly what kind of signal is being sent, so it can send another signal that is going to be reflected through this reflecting surface, and that can arrive with the perfect phase shift to cancel essentially this reflecting, this interfering signals. So here we are using the reflecting intelligence surface to basically cancel or reduce interference, and as such improve the signal to interference plus noise ratio. Okay, so that's one important technology that we'll probably see as part of 6G. Another important technology is what is known sometimes as extreme bandwidth communication. This is communication operating in the very high end of the spectrum. So people are talking about exploiting terahertz band. That's a band in between millimeter wave and optical band. It has some interesting potential. It's available. It has a lot of available bandwidth, and it can basically allow to transmit at super high speeds. Obviously, coverage is limited. It's short range, so one has to use either reflecting surfaces or multi-hopping to be able to achieve longer coverage. But some of the applications are anyway short range by nature. If you are looking at cable replacement approach or indoor communication, some of these can just live with short range communication. Obviously, as I mentioned as part of my introduction, you can push the wavelength, the frequency even higher and reach the optical part of the spectrum, and then you can start talking about free space optics or visible light communication, or even non-line of sight ultraviolet communication to communicate at super high speed in these optical bands. In a way, it's like having an optical fiber in the air. So instead of having a cable, you are transmitting or using a laser to transmit at super high speed on the air. So these are some of the basic principles behind free space optics. I will try to kind of not go through details. And by the way, these slides, I will make them available to the organizers, Mr. Nader, and he has full freedom to share these slides with all of you in case you would like to look at some of these reference or read more carefully some of these slides. Now let me go to the second part of my talk over the remaining 20 minutes or so, which is how to connect the unconnected. I'm calling this connecting the base of the pyramid. So what I mean by that is one way to categorize people living on Earth is by their income. And actually, when you do that, and this is like a famous paper done by some scholar in economy, they were able to show that people who are basically earning a very little amount of money is like nowadays, let's call that like $1,500 per year, constitute actually the base of the pyramid. These are the majority of people on Earth. And these are the people that tend to be unconnected. They represent a huge market. Connecting them can also create much better equity and basically kind of reduce inequalities. So if you look at, for example, how 2G is spread in the world, that's what you get. That's how 3G looks like. 4G, if you put everything together, you get that. Now, as you see, there is a big holes. There are a lot of dark zones. And obviously, the objective is to try to connect more of these dark zones because these are basically areas that are very much underconnected. So if you want to go to numbers, this is what we have here. So we have basically countries that are very well connected, like you look at Europe, North America, reaching percentage of 90% to 100%. But then you go to, for example, Africa, and you see that there is a lot of countries that are either not connected or underconnected. So this kind of issues known as digital divide are due to many kind of reasons. Number one, you can think of basically the business aspect of things. As you know, when you look at mobile network operators, they when they look at their network, the way they can make money is by basically deploying their base station in the area where there is a high level of population, or where basically there is a high density of population. Obviously, it doesn't make much business sense to lay kilometers, I mean hundreds, thousands of kilometers of fiber to reach a very remote and basically sparsely populated areas. That's one of the main problems why we are not able to connect remote regions or rural regions. Another problem is we tend to forget that to have reliable communication networks, we need to rely on a reliable, let's say, power grid. This is sometimes not available, or if it's there, it is really not reliable. So these are some of the reasons that essentially we end up with these bad statistics. And by the way, when we talk about digital divide, we are not talking only about remote rural areas. It can be in some of the mega cities where basically there are some slums or low income neighborhood where basically connection are either not available because mobile network operator don't find any benefit in connecting this low income neighborhood, or because the connection is there but is quite expensive and people cannot benefit from it. So this digital divide affects rural remote areas, but affects also low income neighborhood or slums within mega cities. So we hope that another important mission of 6G is to bridge digital divide. Is basically, this hope is that there is some cooperation between different structure, different organization to bridge this digital divide and to bring reliable internet to those who are not able to have it now. This can help essentially bring better health services, better education service to remote regions, And it can allow to break this vicious cycle of digital divide, where basically you have, it's like when you kind of choose to kind of build a road or a highway connecting a remote region, and then obviously you can bring prosperity, you can bring economic growth, you can bring better service, you can kind of incentivize people to live in these remote areas. So the same thing can be done by creating these information or building these information highways. We wrote recently a paper that appeared in this month, actually April 2020 issue of Proceeding of IEEE, where essentially we survey all what has been done, or at least a lot of the things that have been done in the context of bridging the digital divide from a communication perspective. So in a way, what we are aiming to is to move out of this kind of very narrow smart city concept to something a little bit broader, which is smart living, like a smart village, smart rural areas, smart remote regions, where basically people can enjoy and their connection and what comes with it, even if they are not living in highly urbanized environment where basically, for example, 5G is planned to be developed or planned to be deployed initially. So let me now go briefly and quickly, just to be within time, about the technology insights for rural connectivity. So obviously, one aspect is power supply at the network level through, let's say, renewable energy, but also to charge cell phones. There are a lot of interesting research that can develop basically solar powered or renewable powered network, so that basically we don't have to rely on an external source of power in remote areas. Another interesting kind of research direction is backhaul. And in particular, when you have a light density of population, the best way to bring a backhaul is through aerial connection, through what people call HAP, high altitude platform, or of course, satellite. So HAP solution are solutions that have been pursued recently by Facebook and by Google. The idea is that essentially you create a network of base stations in the air that are going to have a certain coverage area, that are going to be interconnected the way base stations are interconnected on the ground, but because they are operating at a high altitude, they have a much wider coverage. Now, obviously, if you have even lighter population density, then you go higher, and when you go higher, HAP operate roughly 20 kilometers above the ground. If you want to go higher, then it becomes satellite, and you go all the way from LEO satellites to GEO satellites, and there is a kind of a big revival of this industry over the last few couple of years to bring global connectivity. So there is a race between different projects trying to bring internet worldwide through different constellations at the different level, LEO, MEO, and GEO, with of course GEO being those who have broader coverage with the least number of satellites, but come with a huge or relatively huge delay, and LEO being the ones that are closest to the ground, lower subject to lower delay, but obviously you need many more of them to be able to have global connectivity. Now, one of the topics we have been looking at KAUST is next generation of satellite communication system, or next generation of very high throughput satellites that rely on one hand on free space optics to connect the satellite to a gateway station on the ground through optical feeder link. And then on the other hand, you have multiple beam RF links to connect remote users in different regions of the world. These are satellites that are expected to be deployed by 2030. They are interesting because they're hybrid. They contain some optical components and some RF components, but they are supposed to bring, a very high throughput. When we say very high throughput, we are aiming like a throughput of 1 terabit per second. Obviously, as soon as you start relying on optical feeder links, it gives you this super high capacity of terabit per second, but it comes with a problem, which is as soon as you have a cloud on the way that blocks this free space optics links, then obviously you need to rely on what we call site diversity, multiple optical gateway stations on the ground to make sure that essentially if it's blocked in one link, you can recover the signal from another link. Now, once you are on the ground, the way you distribute internet, you can reuse TV tower kind of infrastructure. These are high tower that can use the opportunistically VHF, UHF band to have tens of kilometers of coverage. You don't have TV towers, you can rely on tether balloon, tether UAV. The tether here can give you basically the ability to communicate without having to recharge the drones or the balloon for a long duration of times, and it gives you the height that comes with a tower in case you don't have a tower. You can also use integrated backhaul access solutions. These are multi-hop solutions that can allow you to let information or packet propagate on the ground from one access point to the next without having to deploy a cellular network. So to conclude, or like some of the last slides here, if we think that we are operating in this kind of world today, then step by step, if we start connecting the dots, we are able to eventually, hopefully by 2030 or so, to leave or to reach a much more connected world. Now, let me conclude by kind of going quickly through some potential applications. So once you have a connected world, for example, e-health can be one big benefit from that. So one of my colleagues here at CAUT, Professor Mohammed Hassin, has been doing chronic low-cost monitoring of asthma, and he's replacing these sophisticated multiple hands of dollar stethoscopes by a very simple do-it-yourself kind of acoustic sensor that essentially resonate at the peak frequencies and essentially can be used to detect patients who have asthma. So it's a very cheap device. If it's connected via Bluetooth to an access point, then basically, and this access point is backhaul to a close by city where doctor is there, then essentially you can monitor remotely many patients that are suffering from asthma. Obviously, emergency connectivity, we all enjoy connectivity in normal situations, but we tend to forget that this connectivity can be lost, or the capacity, like nowadays, you know, we are facing a problem where more people are working from home, so more capacity is needed in some areas. When we develop technologies that allow to beef up capacity, to bring capacity to areas where connectivity has been destroyed because of natural disaster, then obviously any kind of research done in this like rural connectivity or remote connectivity can be reused in the context of emergency connectivity. So this is known in general as pop-up network, the ability to beef up your capacity as needed in disaster emergency event to bring extra capacity in the case of World Cup or concert or sport event, bring capacity in remote areas for scientific mission purposes or for military mission purposes. And when you talk about pop-up network, the main research issues one has to solve: backhaul, how can you reach these remote areas sometime through satellite or through hubs, for example; spectrum access in these remote areas through integrated backhaul access, TV towers, you know, high altitude tether balloons; how to supply power through renewable energy, and how can you quickly deploy this structure in the middle of nowhere sometime. At the end, one benefit of having global connectivity that is initially aimed to connect people is that you'll be able to also connect all kind of devices. So as soon as you start connecting all kind of devices and sensors, you can basically develop new climate models, because in real time you can gather data from the underground, from underwater, from different regions on the earth, and we can have all this information fused into you know, central data centers and come up with better and better, let's say, climate models. So with that, I would like to kind of wrap up my talk and have this concluding slide with this quote from Nikola Tesla, done about 100 years ago, where basically he had this very nice vision on how wireless can be used to connect seamlessly the world. And we are now at a time where we are converging towards this vision. So it was kind of impressive or amazing to see this visionary statement made by Tesla about 100 years ago kind of make quite a bit of sense in today when we are thinking of 6G, of 5G deployment and the design or the, let's say, the perspective for 6G. With that, I would like to thank you, and I would like to open the floor for questions.
So thank you, Dr. Mohammed, for this informative and amazing talk. Now we'll like to tell our participants to use the raise hand button if they have a question, or send their questions via chat so we can ask it to Dr. Mohammed directly. Here we have a question from Ammar Sarur. Ammar, yes?
First of all, hello, Dr. Mohammed. What a great lecture it was. I have a question regarding 5G towers. 5G, or what we call them, cell towers, if I'm correct. We call them cell towers because it uses so much high frequency, so we need like small towers close to each other in order to maintain the signal. But 5G network use so much high frequencies, up to 10 gigahertz or 20 gigahertz, which is much more greater than 4G. And if we use 6G, it's also going to be much higher than 5G. You said in terahertz band. So isn't it going to require really small distances between each tower?
Yeah, I mean, it's a combination. Obviously, not everywhere we are going to have super dense deployment. In certain environment where there is a very high density population, you may need to go to a higher density of access point deployment in the millimeter wave range or terahertz range. But when you go into areas where the population density is much lower, where like population is much more sparsely distributed, then you don't need that. You don't need to go for these super high frequencies. Actually, on the contrast, you want to go more for UHF, VHF to have a big coverage in the lower part of the spectrum. So it's a combination of this and that. And obviously, the higher is density population, the more you need to reuse the spectrum, and the more this lends itself to using higher frequency with short propagation requirement.
Great, thank you, Doctor. Here we have a question from the chat. It says, how does 6G will improve the spectrum efficiency?
I mean, in a way, large intelligent surface, ultra-massive MIMO system. So massive MIMO is one way to increase spectral efficiency. You try to increase the number of beats per second per hertz. And one way to achieve that is to use multiple antennas. So people are claiming, or at least are aiming, to go from what we have today, which is MIMO, some people call it maybe massive MIMO to a certain extent, to ultra-massive MIMO, hundreds of antennas used in the base station to be able to multiplex many more data streams within the same connection. So one possibility is that. Large intelligent surface, in a way, improve also spectral efficiency, because that's one way they can be used to multiplex more data within the same area of coverage.
Great. We would like to remind you, ladies and gentlemen, that there will be a prize picked from the best tweet on our hashtag #Sharikna_IEEE. Now we will take a question from Mr. Muhammad Al Hussein. Yes, Mr. Muhammad?
Do you mean Muhammad Hassoun?
Yes, I'm sorry.
No. Thank you very much, Professor Mohammed, for your nice talk. I'm curious about when you have multi-surface or meta-surface how would you, I mean, would those affect the signal coming into buildings? Because as I understand that you're going to, I mean, the vision is to coat buildings with those services. How would that affect the RF signal coming into the building, say for voice or other applications?
I mean, so, as you know, the spectrum is divided to different pieces and parts. So, I mean, some of the spectrum is going to be used for, let's say, to communicate with outdoor users, and some of the signals that are going to be transmitted towards these reflecting surfaces are going to essentially be bounced back or reflected with these phase shifts toward users that are in some nice spots, at least with respect to this intelligent reflecting surface. But obviously, I mean, all of these signals can also create interference. I'm not saying that doesn't come with interference. So, but I mean, it's like any base station you can have when a base station or a reflecting surface transmit a signal or reflect the signal. Part of it is going to be desired for the people who are expecting the signal, but part of it is going to be also interference. But we know how to deal with that. There are mechanisms to cancel interference. There are new multiple access scheme like NOMA that kind of allow a certain level of coexistence between users that can interfere with each other. So this is like standard kind of ways of, as you know, when you do communications, we are always having a desired signal and interference, and we have to deal with that.
Great. Doctor, do you have time for one more question?
Yeah, go ahead.
So a question in chat says, what about creating a communication protocol as chain block where users' devices have the ability to RT as a network?
I mean, of course, there are a lot of interesting ideas. Blockchain is actually an emerging field for security, for authentication, and so on. So, I didn't think specifically about this topic, like how you can create a network with users that, but it can be an interesting research topic to be investigated. And maybe I'm not an expert in this. I'm not kind of active in this connection between blockchain and communication, but maybe there are some people who are already thinking and kind of researching along these directions.
Amazing. Thank you all for participating today. We are sorry we cannot take more questions as to not take too much time out of the doctor's schedule. We thank you for participating, and we would like to remind you that there will be prizes picked out of the best tweet on our hashtag #Sharikna_IEEE. Thank you all.